As we enter deeper and deeper into the digital age, we find that much of our daily needs and activities are driven by technological devices, fundamentally powered by things we call computers. But what exactly is a computer? Essentially, a computer is a machine that can carry out sequences of processes to produce an output based on an input. Early computers were only used to automate calculations, but modern computers now can do a variety of functions. Computers generally consist of three main parts: a processing element, typically in the form of a CPU or a microprocessor, with memory to carry out assigned operations and calculations, an input device used to provide information that is to be processed, and an output device to show the result of the processing. Despite us capable of giving input information in our language to be processed by the computers themselves do not work in the same language as we do. They use the binary system as their primary language. The binary system represents information using only a pattern of zeros and ones. The positions of the 0 and 1 in an 8-unit long string determines their respective values in powers of 2, as in the first position being 128 followed by 64, 32, 16, 8, 4, 2, and 1 in order, which all correspond to 2 to the power of 7, 6, 5, 4, 3, 2, 1, and 0. For example, letters that we use can be represented in binary such that it can be understood by the computer. As an example, the lowercase a can be represented by the string 0, 1, 1, 0, 0, 1. Most modern computers use binary to encode instructions and data in a way that can be sent and understood by other computers. As mentioned previously, computers carry out sequences of processes to get from input to output, keyword being sequences here. Computers carry out actions exactly as they are programmed to do, which means that a robust flow of instructions are necessary to ensure that the desired output is reached considering all possible input. This flow of instructions is what is called the algorithm of a computer, an exact set of instructions and rules on following those instructions given different scenarios. Computer algorithms can be visualized using the use of block diagrams, which draw pathways and appropriate decisions to be taken by the computer during processing, based on the parameters of the input received. Shown here is an example of a block diagram in a complex calculation program, beginning with the data input, which undergoes a series of checking and processing through complex mathematical equations, generating new variables that are used to finally generate data to be entered into the database as an output. More complex computers have even more complex diagrams that may be split into different parts for simplicity. The use of these diagrams helps outline the processes needed, making it easier for programmers to create the code and for users to understand the program as they use it. As an example, here is a program using the Python high-level programming language whose goal is to generate a graph that plots elevation or height against time for an object that is released vertically at a specified velocity given the gravitational acceleration. Shown here is the lines of code used. The first two lines correspond to importing other libraries or a predefined set of code and operations in Python, which can be freely accessed to help us do work easier. In this case, first, the matplotlib module is imported, which is a library of code for creating mathematical visuals, and second, the numpy module is imported, a library of complicated mathematical functions and equations simplified into shorter code. For reference, the mathematical equation that we are referring to is this: y equals to v0 times t minus half of gravitation times t squared, an equation for the vertical displacement of the object that is moving vertically in the presence of gravity. The equation contains three variables, namely v0, which is the initial velocity, g, which is the gravitational acceleration, and t being the time. The next two lines of code serves to assign values to the variables that we need, creating two variables g and v0, which has a constant value of 9.8 meters per second square and 5 meters per second respectively. Since the graph that we want has t or time in the axis, it needs to have multiple values and not just one, That way, we get a graph and not just one line, which is why we use the np.linspace function, which returns numbers at evenly spaced intervals. The two numbers in the bracket of the np.linspace function tells the starting and ending number we want. In this case, 0 and 1 second is enough over 1001 intervals or any random large number to create a smooth graph later on. With the variables assigned, we can input the equation we want into the program, which in this case is the y equation mentioned previously. Next, we instruct the program to run the plot function, which plots values of t in the x-axis and y, our equation, in the y-axis and form a graph from it. At this point, the program has already done the processing, but usually we won't be able to see the graph unless we tell the program to show itself, which we can use by using the plt.show function. A smooth curve of elevation against time is now visible. Using different equations and variables can result in different plots, up to the needs of the user and the input. That is the essence of computers, which generate output using processes based on what we want and what we need it to do.